Welcome to Study Loop.
This is chapter 21, problem number 82. We have two rails on an inclination. So these are the rails, they're resistanceless. Um, and the angle that it makes with the ground is 6 degrees. So at the end of the rails, we have a copper bar. This is the side view, right? So the copper bar extends into the page. So this copper bar is moving with a terminal velocity, meaning a constant velocity. Um, and we're asked to calculate this velocity. Let me give you a couple more details. The magnetic field at which the entire system is embedded in is in the vertical direction. This is the direction of the magnetic field. And we are given the mass of this bar, 0.04 kilograms. We are given the strength of this magnetic field, it's 0.45 teslas. We are given the length of the rails, length of the bar. It is 32 centimeters, so it's 0.32 meters. Now we're asked to calculate the velocity, right? So first of all, we're going to have to draw a free body diagram of the bar, right, which is this guy here. So in this case, if this is a bar, we have the gravitational force acting on this, right? This is the inclination. So then, since this is the inclination, we have the normal force exerted by the surface on the bar. And since we know there is a current in this, well, it's kind of hard to imagine from the side view, but um, there's current flowing through it, so that actually the bar actually experiences a magnetic force, right? So first of all, we need to determine the direction of this magnetic force in order to do so, right? This is F sub B is what I'm talking about. Now, if the velocity of this bar as it slides down it's constant, then could the magnetic force be to the left? No, right? Because if that were the case, then the velocity would be actually increasing with respect to time. So then you can clearly see that F sub B has to be, magnetic force has to be pointing the other way. The reason why it's either to the left or to the right is because remember what this magnetic force is. It's the current times the length times the external magnetic field that is given to us, right? So current either is going into the page or out of the page through the bar. So how are we going to determine this is, well, from the right hand rule number 2. So if the current is out of the page, then using your right hand, you align your thumb with the direction of the current, and the rest of the fingers show the direction of the magnetic field. When you curl your fingers 90 degrees, the tips of your fingers show the direction of the magnetic force. If I is out of the page on the bar, then FB would be to the left using your right hand rule number 2. And this is not acceptable, right? So then the current must be going into the page in the bar. So when the current is into the page, again, use your right hand rule. Your thumb is in the direction of the current into the page. B field is going up. Then curl your fingers 90 degrees. The tip of your fingers show F sub B. So then I has to be into the page on the bar. So that you would have F sub B to the right, so that you would have a constant velocity, right? So if we agree on this free body diagram, the rest is pretty straightforward. So let's use this coordinate system x and y. Then f sub g is purely along negative y direction. and f sub b is purely in the positive x direction, right? And n, though, the normal force is actually at an angle, but that angle is given to us. So on a new page, again, this is the bar. Imagine this is f sub g, this is f sub b, and this is the normal force. However, you know that this angle theta is given to it 6 degrees. So then the x component of this normal force is going to be n times cosine theta, where theta is 6 degrees. And the x component, and that's, pardon me, I called the y component x component, so please fix that. And so y component is n cosine theta, x component then is going to be n sine theta, right? So then we decompose our normal vector. If we write the net force in the y direction, what we have here is n cosine theta is in the positive y direction, right? So then we're taking it as positive. F sub g is in the negative y direction, so negative f sub g here. Now we know that this bar is not moving in the y direction, so it's going to be equal to 0, at least not with acceleration, right? The net force in the x direction is going to be f sub b. There's a positive here, as you know, because it's along positive x direction. And then we have minus n sine theta. Again, this minus comes from the fact that n sine theta is in the negative x direction. Again, we don't have any acceleration in the x direction, so that equals to 0. From here, we have two equations. N cosine theta equals f sub g. N sine theta equals f sub b. Now, n, the normal force, is totally irrelevant for our case. So I'm going to rewrite these two equations here in the order to it proves you something. And sine theta equals f sub b, and cosine theta equals f sub g. So if I take the ratio of these two equations to get rid of the normal forces, sine theta over cosine theta gives me tangent theta. The right hand side is f sub b over f sub g, right? Where, as you know, f sub b is going to be ILB, B being the external magnetic field. F sub g is simply the gravitational force of the bar, right? So if we plug these in this equation, then, we have tangent theta equals ILB over mg. Now, what I want to do is I want to get the current out of this equation. So current is going to be mg tangent theta divided by L times B, right? So this is the current passing through the bar. Now, we know that in this circuit, at the bottom part, on the bottom part here in this part, we have a resistor, right? So we have a resistor. Also, the resistance of that resistor is given to us as 0.6 ohms. The point being, the potential throughout the circuit has to be current times this resistor, right? And we calculated I to be mg tangent theta over L times B. So all I'm going to do is I'm going to put it here to calculate the potential. Mg tangent theta over L times B times R, then is going to give me the EMF, right? The voltage throughout the circuit. Also, now let's look at it from the perspective of the moving bar. As you know, as the bar moves downward with a constant velocity, the flux is decreasing with respect to time. So when that happens, the induced EMF by this moment is B times L times V for that particular circuit. Now, if that's the case, then again, remember we were trying to get to the information about the velocity. So then if I divide both sides by L times B, I have the velocity term. So mg, let me put r here, tangent theta over L times L is L squared. B times B is B squared. Then there you go. All we need to do now is to plug in the numbers. So again, the mass was 0.04 kilograms times 9.8 meters per second squared, right? Gravitational acceleration. R is the resistance, is 0.6 ohms, and our angle is 6 degrees. Divided by L was 32 centimeters, so let's convert that to meters, and then we have B squared, so 0.45 Tesla squared. Then our velocity, the speed happens to be 1.2 meters per second for our copper bar.